In this segment, we're going to talk about the general, we're going to go a little deeper into the setup for reading comprehension and talk a little bit about baselines that we might imagine, which is going to help us think about how to design the neural net models that we're going to be using for this task. So we've got here a passage with two sentences in it. This is something we call the passage or the context. It's sort of what we're answering questions from. The assassination of Franz Ferdinand led to World War I. Gavrilo Princip killed him on June 28, 1914. And the question is, what event led to World War I? All right, so we have a few different baselines that we might think of in terms of how to answer this question. And these can draw on various ideas that we've seen so far throughout the course. So one idea is to say, all right, we've got basically a kind of X led to World War I sort of pattern that we're looking for. And what we want to do is then we take various windows of the context, like, maybe we look here and here and here in one sentence, and then, here, 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 here. And we intersect the set of n-grams from the question with the set of n-grams from the passage window. Right, so essentially what we're saying is we need to find something related to led to World War I, and maybe if we're lucky enough to grab this up here as our window, then what we'll see is, oh, okay, great. We have this nice overlap between X led to World War I and the assassination of Franz Ferdinand led to World War I. And so assassination of Franz Ferdinand, that seems likely to be the answer. Okay, so we'll call this the sliding window method. And we can also think about doing something similar using syntactic parsing. So if we parse the question, I'm going to write this in a sort of reduced dependency representation here. We can get something that looks like this, where we're looking for something that led to World War I, right? And ideally, what we should be able to see is that in the passage, we also get led to World War I, and then we get the rest of the kind of dependency subtree over here. And by comparing these two things, we recognize, okay, we can sort of bind X to this subtree over here and therefore get the answer. All right, so this looks like a slightly smarter way of doing things than the sliding window method, and we'll call this the parsing-based method. All right, so one issue is, what if we, instead of saying led to, we say caused World War I? Then suddenly the n-gram sliding window doesn't look as effective. And the parsing technique, again, we didn't actually talk about how to do this comparison or matching, but again, we're relying on word match here, and we generally need to do something smarter than that. So this is where neural nets come in, and we are also going to try to make our framework a little bit more general than tying it to sliding windows or syntactic constituents. So this gets us into the span extraction paradigm that we mentioned earlier. So Here, I'll reproduce our sentence. And we said that this was our answer. We wanted to pick this out as the thing to show to the user. And so if we think back to NER, we can use a BIO tag set like we did there. Recall that what's going on here is that we're saying, okay, we're going to tag each word with a tag that where O says you're not in the answer at all, right? B answer says that you begin the answer, and I answer says I am continuing a span that is the answer that started with B answer. So this is the span start, and this is the span end. Now, one difference from NER is that we only want one span here, right? In named entity recognition, it was generally fine to have multiple named entities in a single document. That's okay. But here we want to pick the best one. So our model is generally going to be a function of a document and a question, and is going to return a start and index pair. And the models that we're going to look at are going to place distributions that look like this. We're going to get a pair of distributions that are basically have the range, let's say 0 to n, where these are the indices in the document that we're considering. And essentially, it kind of represents where the answer is likely to start. And so maybe there's a couple of different possible answers. And so the distribution looks like this for start. And for end, maybe the end model knows that the end has to be here and everything else is very low. And so what we do is we find start end pair with highest probability that aren't too far apart. So what we wouldn't want to do is maybe let's say way down further in the document, you also had a fairly likely end position. You would not want to take this start and this end point and then just like return a massive paragraph or like a whole page as the answer. That's not the right thing to do. Instead, what we're going to say is, okay, these two are reasonably high probability and maybe show up within 5 tokens of each other or something like that. So that's a reasonable answer to return to the user. So even though we're modeling these distributions semi-independently, and this is something that's not really correct, right? We should be placing distributions over like all spans in the document. But because there's a quadratic number of spans, that gets to be intractable. So we approximate that essentially as a basically 2 distributions each over indices, and then we have to sort of ram those together at the end to actually get the final answer. So it's an approximation, but it's a standard one that people make when doing this type of question answering. And so what we're going to talk about next is how to take basically how to build a neural net that goes from a document and a question and maps to these distributions over start and end positions. That's the end of the segment.